Okay, so I wanted to actually, I just recalled that I forgot to say something about our lectures. We, due to the University of Toronto schedule, we will usually start. So now it's 12, yeah, 10. Okay, so on Tuesdays, we start usually at, okay, 1:10 p.m., right? So we'll have 50 minutes on Tuesdays. And on Thursdays, we have 2-hour lectures, 12:10 till 1:00, then 10 minutes break. And then 1:10 till 2 p.m. Okay, so this is our usual schedule. All right. So yeah, this is because of the standard University of Toronto schedule. I just recalled that unfortunately I didn't say this last lecture, but for those who are already here in Toronto, it's the system is quite familiar. So let me. Okay. So today I was going to give some necessary background. Besides, I know that some of the participants are undergraduate students, so perhaps this might make some sense. Okay, so again, yeah, I see the board is here. Okay, so what are the objects that we are going to use quite often during this course? We will discuss topological manifolds, smooth manifolds. Also, we will deal with some, well, usually quite specific Lie groups and algebraic groups. And finally, Riemannian manifolds, definitely, since we eventually will be talking about isometries, and those isometries like partially come from Riemannian geometry. Okay, so today I'm going to give some background on topological and smooth manifolds, and probably we'll also study group actions on manifolds in some like broader setting, in the sense of like group actions by homeomorphisms, since this will be, I will give you some fundamental facts from differential topology and just topology, which we will be using in some, well, in proofs of some fundamental theorems. For example, the proof of most rigidity theorem, which I mentioned in the last lecture. It is based on really a lot of such fundamental theorems. Okay, so great. Then, okay, so topological manifold. It will be, for us, it will be a Hausdorff topological space such that it's such that every point has a neighborhood homeomorphic to Rn, right? Homeo to Rn. I've also reminded homeomorphism. So a map F between two topological spaces X and Y is a homeomorphism. if F and F inverse are both continuous, well, and bijective. So, and F is bijective. Okay. This is a like pretty strong equivalence relation in topology. Okay, then okay, so this is about topological spaces. Okay, so like for us, okay, I will remind some other topological constructions later, but certainly typical examples are definitely Rn, right? Open ball. Here I'm already introducing some notations that we'll use here. Open unit, well, open ball Bn. This usually denotes the unit ball, right? So this is B, which I usually denote BO, and 1, which means that this is the center, the origin, and this is radius. Okay. Now, a smooth manifold is again, usually that would be a Hausdorff space M equipped with an atlas of charts. Which I will denote by U alpha by alpha. What does it mean? It means that, okay, for every point, right, for every x in our space M, there exists open U alpha containing x with the homeomorphism phi alpha from U alpha to Rn. And for every two intersecting charts, so, and for every pair alpha and beta, we have the following. The transition maps. So the transition map, which is denoted by phi alpha beta. It is a map from the image of intersection, right? So U alpha intersected with U beta is mapped to the image under phi beta. So let me write it here. So imagine we have such a picture, right? So this is our M, and we have two intersecting U alpha and U beta. So this is their intersection. So under phi alpha, so this is my Rn, right? So it goes somewhere here. And this is mapped. They might intersect actually somehow, but it doesn't matter, right? So, and the image under the second one is this. So now these two guys are sitting in Rn, and so we have some differentiable structure in Rn, right? We have the differential structure here. So this map is basically from Rn to Rn, right? So the image here is sitting in Rn, and here it is also in Rn. So we want these transition maps to be just continuously differentiable. So I will write such that the transition map, it belongs to, let me write it here, to infinitely differentiable maps on Rn, okay? So our manifolds will be actually smooth manifolds. Okay, this is, so again, typical examples are again, Rn, any basically simply connected open domain in Rn can also be considered as just a smooth manifold with one chart, right? Let me consider something more interesting. I can take Sn minus 1 sitting in Rn. It will be an n minus 1 dimensional smooth submanifold of Rn, right? Any hyperplane in Rn will be thus a submanifold in Rn, and so on. Okay, there is sometimes the submanifolds can be defined by some system of different, I would say, like some system of equations, right? Those equations can be polynomial and can be not generally. So for example, Sn minus 1, it is determined by just one equation, right? It is determined by the coordinates x1 and so on xn, such that x1 squared plus xn squared is equal to 1, right? By if you have some number of, or more generally, m can be the set of points such that we have some system f1 of x is c1 and so on fk of x is ck, right? So this is another type of, like, this is a general type of manifolds, well, of submanifolds in Rn. One can, to compute the dimension of this, one need to basically differentiate every equation, and you will get the system of linear equations, right? And then you find the rank of this system, and this basically gives you eventually it gives you just the tangent space to this submanifold in Rn. We will get back to this discussion a bit later when I will talk about Lie groups, since there it is useful to determine the dimension of a Lie group. Okay. So yeah, this is our these are our examples. Okay. I also wanted to say something about. Okay. Yeah. In fact, we will also sometimes we'll also deal with manifolds with boundary. So a smooth manifold M with boundary is a manifold with knotless containing two types of charts. With an atlas with two types of charts. Okay, so I will denote them by alpha. So the first type is the standard, right, to Rn. And the second type, I don't know, I think I used some notation. Okay, no, I don't have any nice notation. So let me use probably psi beta, and I will denote this by V beta, and it goes to Rn plus, I think. Let me denote it by Rn plus. So it is still OX. It is a half space. So the last coordinate xn is greater or equal than 0, right? So this is my second type of charts. Okay, and with the same condition as there, yeah. So with the same transition condition. Okay, so for example, this is definitely the half space Rn plus, right? It is definitely such an example, but of course we have some more interesting examples. Let me. Okay, I do not want to move there, but probably I will have to. Okay, so I'm going to use this blackboard. Examples with boundary. So, for example, the closed ball. The closed ball, which I will just denote by Bn bar, which means that it is the open ball Bn with its boundary sphere. It is definitely a manifold with boundary where dBn is just this n-1 dimensional sphere. Okay, well, the trivial example is just so the example number 0, it is just Rn plus, okay? So definitely you can just take one chart, or if you would like, you can cover by, so all interior points you can cover by open balls, and then only for the boundary points where the boundary is just the hyperplane, right? So G, Rn, sorry, I changed the indices. So GRN plus is, of course, just Rn minus 1. Okay, so here we see that the dimension of the boundary somehow happens to be always of codimension 1, right? Of dimension n minus 1. And indeed, there is the following like theorem or lemma that if M is an n-dimensional smooth manifold with non-empty boundary, non-empty boundary, then Dm is itself a smooth manifold of dimension n minus 1. It is an n minus 1 dimensional smooth manifold. Okay, another interesting fact, I will not write it down here, probably I will mention it later, that if it is actually an orientable manifold, then orientation also passes to the boundary, right? Okay, so again, our example sphere Sn are pretty nice. The sphere itself is the manifold without boundary, right? Its boundary is empty. Okay, so what's next? I also wanted to like just to remind a little bit about, I think, yes, for now about, so from just topology part, I will probably need homotopies and fundamental groups. So yeah, let me remind this as well. Okay, so now let X and Y be, okay, let them be just, I think, topological spaces. Let me think about of how much generality I want. I have some plan. Yeah, okay. Okay, I think this is fine. Yeah, so we say that two continuous maps F and G between two topological spaces X and Y are said to be homotopy equivalent, or just homotopy to each other, and we will denote it. So the notation will be F tilde in this horizontal bar G. I don't know how is it called. Then it is, so if there exists a continuous map H of S T, I always forget, I always forget which, yeah, okay, so the first part goes for my maps. Okay, yeah. So this is a map from X product, the segment, yeah, right, to Y. So this kind of the cylinder, right, such that H of I think I can just put here X, right? So H of X 0 is F of X, and H of X 1 is G of X, right? So one can think of this as just like a continuous deformation of one map into another one, right? Okay, then it is a good, it is a very nice equivalence relation. So some facts about homotopy, right? So any F is homotopy equivalent to itself. So the first property. The second property is that if F is equivalent to G, then definitely G is equivalent, homotopy equivalent to F. And if F is homotopy equivalent to G, G is homotopy equivalent to some another map H, then F is homotopy equivalent to H. right? So this is symmetric, and we have the transitive property. Okay. Another, maybe I need some example. Okay, I will think about this a little bit later. So yeah, I didn't actually, okay, I said, but I didn't write it down here, right? So this is continuous. So interpretation is a continuous deformation from F to G. Okay, important fact is that, yeah, I want now to define homotopy equivalence of spaces, and this will already be partially used in the proof of most of rigidity, actually. So let me erase here. Okay, so topological spaces X and Y are homotopy equivalent if there exist the following maps. So if there exist continuous maps F from X to Y and G from Y to X, such that the composition of F and G, right? So we first apply G from Y to X and then back from X to Y. So it is a map from Y to Y. I want it to be homotopy equivalent to the identity map in the space Y, and G composed F is homotopy equivalent to the identity on the space X. Okay. In this case, the topological spaces are said to be homotopy equivalent, and again, we will also define it by using the same symbol, right? Okay, so there is the following theorem. By the way, I did not introduce the notation for homeomorphisms. Okay, let me just change for a little bit to the left. So when I say that a map F is a homeomorphism, homeomorphism will be denoted by double tilde notation. So I will just simply write that X is homeomorphic to Y. Okay, so we'll use this notation for homeomorphisms, and we are using this notation for homotopy equivalence. Great. Then certainly if X is homeomorphic to Y, it implies that X is homotopy equivalent to Y. But the converse is not true, definitely. So an example, right? So for example, Rn is homeomorphic to an open ball, and it is homeomorphic to, okay, and Rn is homotopy equivalent to the point, right? But it is not homeomorphic to Rn, right? So the point is homotopy equivalent to Rn and to, so basically any open ball, any Rn is contractible to the point. So we say contractible to the point if there is a homotopy equivalence between the space and the point. Okay, or we just say contractible. Okay, so this is again, so the manifolds, as I told you, manifolds that we will be mainly discussing here are hyperbolic spaces and hyperbolic manifolds. The hyperbolic spaces themselves will be just homeomorphic to Rn. So in the sense of topology, it will be basically the same. But in the sense of geometry, they will be quite different. All right, so this is about homotopy equivalence. Now, by the way, I mentioned, so on the last lecture, I mentioned one of the examples. Okay, let's discuss this example a bit later. Since I wanted to, what I wanted to introduce is the notion of fundamental groups. Okay, so this will also be the definition. So okay, let M be okay. For now, it is again is just a topological manifold, but generally we can think of smooth manifolds. So let M be a manifold. Then a continuous path joining points. Okay, how will we denote them? P and Q in M. It is just a continuous map, which I will denote by gamma from the segment 0 to 1 to M, such that gamma of 0 is P and gamma of 1 is Q. Okay. Again, we can, since we have now we can consider different continuous paths, and some of them can be homotopy equivalent to each other in such a way. So we can consider homotopy equivalent continuous paths with fixed endpoints, right? So like geometrically, it's something like that. This is my gamma of 0. This is my gamma of 1. Okay. All right. So now a loop is just a path with the same starting and end points. So a loop is a path with gamma of 0 being equal to gamma of 1. So it's indeed a loop, right? So as in the definition of homotopy equivalence, we can talk about homotopy equivalent loops or homotopy equivalent paths, right? Okay, now I want to define the yeah, okay, I don't know how much of the details I need to define, but let me try to make it okay, as rigorous as possible, but on the other hand, without delving more into the just fundamentals of algebraic topology. So okay, I will say that the product, right? So the product, one can define path product. So suppose I have two paths. So 1 is gamma. Okay, gamma 1, 0. Gamma 1 of 1 is equal to gamma 2 of 0. So I'm assuming that there are 3 points now, right? P, Q, and S. Maybe S is not good, but let it be R, okay? So 3 points, P, Q, R. So the path gamma joins P and Q, and gamma 1 and gamma 2 joins Q and R. Then I define the gamma, okay, gamma 1 product, gamma 2 of T. Maybe can just go for loops. No, okay, I will define it for then, and I will say about loops. So, yes, it should be, okay, it should be gamma 1 of 2T, and here it will be gamma 2 of, I think, 2T minus 1, but let me just check. So if T belongs to the half segment, right, from 0 to 1 over 2, and here T belongs to the remaining part, 1 over 2 to 1. Okay, let us check. If T equals 1 over 2, then it is gamma 1 of 1. If T, so yeah, sounds correct. Okay, so eventually I hope you see that we get then path, right, which basically repeats our path. It passes through the midpoint. It's kind of the midpoint of this path here from the point P to R, right? So it is a new continuous path, like a combination of these two. Okay, so in the same way, like as a special case of this path product, one can consider the products of loops, right? Okay, so basically, actually, and by the way, the inverse path, one can also define the inverse path with respect to this path product. And the inverse path, let me write it here. So the inverse path gamma tilde of T is just gamma of 1 minus T. So basically, it's just the way back from, so if you go from P to Q, then the gamma tilde goes from Q to P. Okay, this is why all this is important. In fact, if we have a pair, okay, yeah, so I will leave it, I think, here, and then I will move to the right board. Yeah. So if we have okay, I will write it as lemma. If we have gamma gamma 1 homotopy equivalent to mu 1 and gamma 2 is homotopy equivalent to mu 2. So let me draw pictures, right? So I have P and Q. This is my gamma 1. And this is my gamma 2. And another pair is, it goes the same, yeah, through the same points. It is my mu1 and mu2. So this one is homotopy equivalent to this one, meaning that there is a continuous deformation, like moving this path to that one, right? So one can think that you continuously deform this path into that one. Then actually the path product is also homotopy equivalent to the path product. These facts basically tell us the following, that one can think of one can fix the point. So the theorem is that, okay, so let P be a point in M, then the set of homotopy classes, homotopy equivalent classes of loops, homotopy equivalence classes of loops starting, right, starting and ending in the point P, form a group which is denoted by phi1 of M and P. And this is and this group is very important for our course, since we will study the fundamental groups of hyperbolic manifolds, and those will act by isometries on their universal cover. Who is this universal cover, right? In fact, it turns out that one can find the simply connected space that covers our space X. But before we go into this, I want to say something about the properties of fundamental groups. In fact, if M is path connected, then phi1 of MP does not depend on P. So it is going to be isomorphic to phi1 of MQ for any Q, right? For every Q in M. And the idea of doing this, right, is that if we had the point P, we had loops and then we have another point, how to make this isomorphism. I know that it is path connected, so that means that there is a path from Q to P, right? So then I can just go this way. I can go from Q to P, make any loop, and go back, right? So this will give me, and vice versa. Yeah, this is important that they can do the same here. So if I have continuous loops here, I can go from P to Q, and yeah, so roughly the idea is here. Okay, now about the examples I was talking about. I will formulate them in the sense of exercises. Like, okay, I will state them as exercises. So prove that pi1 of the unit circle is just z. It is natural. It is quite natural, since if you have a circle, basically you enumerate, you kind of encode your loops by windings around, right? By windings around the circle. Okay, another example, sorry, another exercise is a torus. So let us consider a torus S1 versus 1 topologically, right? So we have this donut, and pi1 of this donut is actually the product of, or the direct sum of these fundamental groups. It is just z squared, right? Which is isomorphic to z plus z, or z times z. Okay. In fact, this is based on something which I did not. Yeah, I didn't mention the following fact, which is also quite fundamental, that if we have the direct product, then pi1 of the direct product is just isomorphic to the direct product of pi1s. And another important fact is that if we have the so-called wedge of, meaning that our two topological spaces are attached along one common point. More, it should be defined a little bit more rigorously, but I have x and y, and basically we have identification of one point in x with another with some point in y, and this is kind of my wedge, right? It's quite an abstract operation, but it turns out that the fundamental group of this thing is the free product of these two fundamental groups. And the fundamental fact, actually it should be number 0, I'm sorry, but if x and y are homotopy equivalent, then their fundamental groups are isomorphic. Yeah? So if x and y are homotopy equivalent, then pi1 of x is isomorphic. By the way, isomorphisms of groups will be usually denoted by this, right? So this is isomorphism of groups. So, okay, this is this important theorem, and I leave a question, exercise number 3. So yeah, we have just 1 minute before the break, and this exercise is the following: take a torus without, so once punctured torus, and find its fundamental group. This example will appear later in the context of universal covers and again, and hyperbolic manifolds and so on. But this can be done without any hyperbolic geometry. Yeah, so this can be done basically just using some topological tools, which I recalled during this lecture. So like this knowledge is enough to make the conclusion. Okay, so now we are going to have 10 minutes break, and we are going to continue at 1:10 p.m. Toronto time. Okay. If you, of course, if you have any questions, please ask or write in the chat. I am ready to respond. Okay. Okay, so yeah, we are going to continue. I will say a few words about aspherical manifolds, since we will also be using a couple of facts later. And the manifolds that we are going to consider during this course, most of them will be actually aspherical. Okay, so let me, yeah, so I will be using this right side. Okay, great. Now, so we defined fundamental groups. Now we will be talking about coverings and probably group actions on by homeomorphisms. Okay, so yeah, I will define covering maps. So a covering map it is actually I will consider the following set of objects. So is defined as follows. We consider set E, which is called the total space, B, which is base, then generally it is called F. It is usually denoted by F, but we will denote it by D, since it's going to be a discrete set. And P is a projection. Where, right? So where P is a continuous map from E to B. So I will denote it by that, right? So this is my E. So P is continuous from E to B, right? It is a continuous map. Such that for every point in B, there is a neighborhood whose preimage is homeomorphic to the direct product of this. So basically, this like it looks like a disjoint union of these neighborhoods. So we will do it this way. So such that for every B, there exists a neighborhood, right, open, containing B, with the preimage of U being homeomorphic to U cross D. So D usually is, right, D is basically C, or it is a finite Z over Zn. Let me write it here. So one can identify it with a Z or some finite set of elements. Okay, but it's not, I would say it's not like enough, since I want to, okay, so the picture is like that. For every point here, for every point here, we have a neighborhood such that it lifts to the total space in the disjoint union of homeomorphic neighborhoods, right? But it should be well defined in the sense of projection. So we in fact have the following commutative diagram. So we have this property, and then we have U times D here, here, and here, right? So the following diagram is a commutative diagram. I wanted this to be discrete. Yeah. Yeah, I think it's for manifolds. Yeah. Yeah, yes, generally it's uncountable, but okay. Yes, it is. Okay, I agree. Maybe this is not a very good comment. Okay, I will write it that in our situation, okay, we will usually have, okay, I will write it this way, right? We will usually have, maybe I should remove it. Yeah, since in fact it is something. Yes, yeah, I agree. Okay. Yes, I agree. Yeah, thanks for the comment. In fact, what I just needed is that it is something discrete. More generally, it is the construction of the so-called fiber bundles, where F can be basically any, and it is called fiber, right? But we do not really need fiber bundles, but we need covering maps. So and so with P inverse of U being homomorphic to U times D, and the commutative diagram, right? And the commutative diagram. Basically, this means that it is okay, like to go to pi inverse of U using through this homeomorphism, and then go to U, and it is the same as to just naturally project onto the first factor, right? So this is this this notation of commutative diagram. Okay. Now I think I want to state the following theorem. In fact, any homotopy in the base lifts uniquely to the homotopy of the okay, let me. Okay, I think I just will state the following theorem. If H is some subgroup of the fundamental group of my space X, then so let H be a subgroup of the fundamental group. This is a subgroup. Then there exists a covering H tilde, sorry, X tilde, such that, right, X tilde, sorry, I denoted by H tilde, but it should be X tilde to X. Okay, such that so eventually it will be the fundamental group of X tilde is going to be H. But this notation means that I indeed need to lift the homotopies, right? I need to lift the homotopies to the covering. And this implies that there exists the universal covering. So such that this fundamental group is identified with H. In particular, there exists a universal covering X tilde to X such that okay, let me also denote it by P, such that pi1 of X tilde is just the trivial group, right? It is identity, and it can be also defined with just the 0 abelian group. And such a space X tilde, it is simply connected, right? Simply connected. If pi1 is trivial, right? So these are called simply connected. And what does it mean this universal? It means that any other covering of our space X can be included. It will be covered by X tilde, right? So universal here means, okay, I have all them here, but universal means that for every covering Y to X, there exists covering map of X tilde to X. So X tilde covers my X, and it covers every Y that covers our space X. Why this universal covering is important? It actually turns out that fundamental group acts on its universal cover properly discontinuously. And now I'm going to define those properly discontinuous actions, and we are going to move to just group actions by homeomorphisms. Okay, I think I will just say, yeah, I will say a couple of words about spherical manifolds, and then we will discuss group actions. Yeah, by the way, as for coverings, so an example is, let me write it down here. Okay, so a picture that I actually draw here, it is an example of a covering of the unit circle by the real line, right? So one can, in particular, this shows that pi1 of S1 is Z. So as an exercise, you can try to define this covering map explicitly, actually. Okay, the second example is the covering of the torus by the Euclidean plane R2. So try to think about this. Okay, now my next definition is that we say that a manifold is a spherical if its universal cover is contractible. Okay, topological space X is spherical if its universal cover is contractible. I remind that it means that X tilde is homotopy equivalent to the point. Okay. In fact, I will just state something about cell complexes, since any manifold can be considered as a cell complex, but we will not be really using cell complexes, but this is Whitehead theorem. So a cell complex X is a spherical if and only if the higher homotopy groups of X are trivial for every K. So order K homotopy groups are trivial for every K greater or equal than 2. So it's kind of determined, right? So it's kind of determined by its fundamental group. And another statement is that if, so I will write it as, so the first part is the Whitehead theorem. The second part is another theorem that if xy are a spherical and pi1 of x is isomorphic to pi1 of y, then x is homotopy equivalent to y, and x and y are spherical manifolds. Again, this part will be used in the proof of the Mostov rigidity theorem. All right. So another statement, I'm not going to write it down, but another statement is that if you have a spherical manifold, then its fundamental group is torsion-free, meaning it doesn't have any finite order elements. Okay, but now let's move to group actions on manifolds. I will say just group actions by homeomorphisms. Okay. Okay, first of all, I will denote, so if so homeo of X is definitely just the group of homeomorphisms from X to X. Okay, so where G is a homeomorphism. One can definitely check, it's not so hard to check that the set indeed forms a group, right, with respect to just standard composition. Definitely we have an identity map, which just fixes every point. And for every G, we have the inverse map, which is our, which is an inversion with respect to our group operation. Okay, now we consider the subgroup of G, and we say that, in fact, I can say the following. G X on X by homeomorphisms if there exists an algebraic, right, a group homomorphism from G to some subgroup G prime of homeo of X, right? So sometimes you have some abstract group, but if you can map it to some subgroup of the homeomorphism group of X, then naturally you have some action by homeomorphisms. Okay, but generally we just think of subgroups of homeomorphisms of X. Okay, then by definition, the orbit space, which is very important for us, the space of orbits or the orbit space or the quotient space. Okay, so sorry, I missed it, but let G be acting, right, by homeomorphisms, right? So Gx on X by homeomorphisms. Then the orbit space X mod G, it is the space of orbits Gx, right, where X belongs to X. So this is our quotient space. We consider, so its elements are just orbits of elements. Definitely we identify, so if two elements X and Y sit in one orbit, they all correspond to the same equivalence class. Okay, the question is, what do you think about the topology of this space? And it can be equipped with the natural quotient topology. So, okay, let me write it down as topology on X mod G is defined as follows. U from, okay, a subset, right? U, a subset of X mod G is said to be open if the preimage, right? If the preimage, which is, I will denote the projection map by PG, right? If the preimage of U is open in X, right? So we have where PG is the projection X to X mod G. Yeah, I hope that everyone sees this. So it is open if it's preimage on the covering, it's basically covering, then it is open. Okay, again, so one can, for example, check that here in this example, right, in this example, we have action of Z as I wrote on the in the first lecture, ZX on R1 by translations. Definitely these are homeomorphisms, right? And this gives the identification of R by Z with S1, right? And you can indeed check that the topology of on S1 is indeed the same as topology on R. It is equivalent to the topology on R by Z. Okay, then another important observation. I will say that the action, okay, I will define this. I will write it here. We say that G action on X is free if every stabilizer is trivial. Stabilizer, usually, yeah, we have two notations, either the stabilizer of X or G sub X, which is the set of all elements of G such that Gx is X is trivial, meaning that it is isomorphic to the identity element in the group, right? Okay, and it is properly discontinuous if, okay, so generally the idea is that if we have for every 2 points, we have 2 corresponding neighborhoods such that kind of their images do not, okay, their images can overlap, but only for finitely many homeomorphisms. Let me write it more explicitly. So if for any 2 points, I have, okay, if for every 2 points X and Y and X, there exist neighborhoods UX containing X, UY containing Y, such that the following set is finite. The set of all elements in G such that G applied to UX intersects with UY. So this intersection is non-empty. And I want this to be finite. So let me draw an illustration. So I have 2 points. This is my UX. This is my, sorry, it is my UY, right? And I want to have only finitely many images of UX. So GUX, okay? So this is my UI here. It is fixed. And I have only finitely many images of this guy with respect to my total group overlapping with this UI. In this case, and if it holds for if for every pair of points X and Y I can choose such neighborhoods, then this action is called properly discontinuous. In some cases, this properly discontinuous action can be reformulated even a little bit more simply, but let me also state the theorem, which is also fundamental for our purposes. Okay, so if G X on a connected Hausdorff space, then the following is equivalent. Hausdorff connected. Then G acts freely and properly discontinuously if and only if the map from X to X mod G is recovering, right? If and only if X by G, the quotient X by G is Hausdorff, and the map X to X mod G is a covering map. Okay, and another important fact is that actually for every I think that for every path connected Hausdorff space, the universal covering is identified with. So, okay, this is kind of the first theorem, and the next one is the following: that in fact, for the fundamental group of X on the universal covering freely and properly discontinuously. Okay, but let me state it a little bit more precise. I will state it like that. So if I have locally contractible Hausdorff topological space, if X is locally contractible Hausdorff path connected topological space, then X tilde mod pi 1 of G, sorry, pi 1 of X is homeo to X, and thus pi 1 of X, which will be usually denoted by gamma X on X tilde freely and properly discontinuously. So in these examples, for example, for instance, in the case of Z acting on R1 by integer translations, we indeed have that the action is free, right? The parallel translations do not fix any point. Only the trivial identity map fixes all points. Otherwise, we do not have stabilizers, and the action is definitely properly discontinuous since basically every I would say that, like, yeah, for small enough neighborhoods, you will actually do not have, where is the definition here? So for small enough neighborhoods, you will probably even do not have overlapping images, right? So you can definitely check that the action of Z on R1 or the action of any integer parallel, every group of integer translations on the Euclidean plane or in the Euclidean space, it acts freely and properly discontinuously, and in fact by isometries. Okay, so here we, I would like to mention this important fact. The fundamental group of nice manifolds acts properly discontinuously and freely on their universal coverings. And again, this will be used later. Now I want to mention a few. Okay, I want to mention one reformulation of the proper discontinuous action. So let me come here. Okay. I will leave it as again, as okay, let it be a proposition, but you may think of this as a problem. Let X be a locally compact Hausdorff topological space. Then the following are equivalent. So the following are equivalent. G X on X properly discontinuously. The second condition is that I want you to reformulate this definition in the setting of compact subsets of X. If for every compact K in X, the number of elements in G such that GK overlaps with K non-trivially is also finite. And I forgot there was another, the third. I think that the preimage, yes. So there exists, so a map from G times X to X times X is actually a proper map. So X times X defined by, so GX, the pair naturally goes to GX. X is a proper map. Is proper. That is the preimage of every compact is also a compact subset. Okay. So yeah, so these three conditions are equivalent. And finally, I want to define the co-compact action. I mentioned this word in the previous lecture, and we will say that Gx co-compactly so definition G x and x co-compactly if there exists a compact subset of x such that G product K, which is basically the union for all G of GK, right? We apply G to K. If it covers the entire space X. Again, there is another equivalent reformulation for this. G on X, X co-compactly. If and only if X mod G, the quotient space is compact, right? And I think I will leave a couple of, again, exercises or examples. Let me, the examples. So again, the actions of, for every n, a natural action of Zn on Rn is co-compact, right? The natural action is co-compact. In fact, okay, let us, for now, it's enough to have this example. It's true for every n greater or equal than 1. Okay, so okay, so now just I think just a few comments. So most of our spaces are pretty nice. So for, I would say, like, for basically for all our spaces, for our manifolds, this proposition holds. So the properly discontinuous action indeed means that there exists, for every compact, we have this condition 2 in this proposition. Okay, so as I told you, our usually our manifolds M will look like quotients of, so the picture, like getting back to our, okay, this is just the comment. So in our course, again, right, in our course, we will deal with the following guys. So we will have M, the quotient of X mod gamma, where gamma X properly discontinuously by isometries. We will discuss isometries and remaining manifolds on the next lecture. And perhaps I will already, so the next lecture, so X will be the universal cover. And however, I will consider also the actions that are not free. So we will consider also groups having torsion. We will have groups that have finite order elements, not only infinite order elements. So for them, the definition of the, I mean, when you have such groups, the definition of the fundamental group is not like that useful. I will probably mention the so-called orbifold fundamental group. but probably a little bit later when we will indeed have something to do with orbifolds. So what is important that this also kind of universal cover X of M, it is going to be a symmetric space G mod K. So now I'm going to, so the plan for the next lecture, yeah, it's kind of stay tuned. Next lecture will be about Riemannian manifolds. Riemannian manifolds, isometries, and Lie groups. And if time permits, I will just give maybe one example of one model of a hyperbolic plane as an example for Riemannian manifolds. And already, probably next Thursday, will be devoted to the introduction to hyperbolic geometry. So we will discuss several models of hyperbolic spaces, their isometries, and so on and so on. So we will go following our plan. But then after that, the plan is to indeed consider hyperbolic, so discrete subgroups of hyperbolic isometries more deeply. We will probably forget for a while some fundamental facts I was mentioning here today, but then we will be using them in the proof of most of rigidity. Of course, we are not very interested to, so some of these facts, for example, for spherical manifolds, I mean, they probably do not appear in, maybe they do not appear in your courses. For example, some of these facts I didn't know when I was a graduate student. So it is actually fine. We will be just using them. We will be more interested in understanding the precise, the facts and the features of hyperbolic spaces. And so we will discuss the boundary of the hyperbolic space, the action on the boundary, the geometry of hyperbolic space that is useful since, again, the most of rigidity theorem is it is very specific for this case. Generally, there are not so many such rigidity theorems. Eventually, so as you might see from some of the examples, there are even manifolds that are very different but have the same fundamental group, right? The most of rigidity theorem states that compact hyperbolic three manifolds and higher are isometric if they have isomorphic fundamental groups. It is a very strong statement, and it's a very strong result. So yeah, this is the plan for the first half of the semester. The second half will be devoted to arithmetic part. So thank you for your attention, and see you next Tuesday.